Okay, so we're going to go ahead and move on to example 4, section 4.1 here. And we're going to look at graphing the what's called the reciprocal function. So we talked inverse functions yesterday. The reciprocal function is exactly this right here. Y equals 1 over x. So this is like an inverse function where the k value is 1. So you have to relate it to what we did yesterday. So this is just the base name, or what we call like the parent function for the reciprocal function. Or some people call it the rational function. It's all kind of relatable words. But anyway, it takes every non-zero real number and maps it to its reciprocal. You know what I mean? So like if you took 2, the reciprocal of 2 would be 1 over 2. Or if you had 3/5, the reciprocal of that would be 5/3, so on and so forth. So the first thing it says, consider the domain of the range of this function. So before we get to graphing or doing anything too much right now, we have an issue here with the domain, because there's a number you cannot put into here because it doesn't work. And that number would be 0. If you do 1 divided by 0, you've probably learned for a long time you can't divide by 0, but even if you try, type it in the calculator, do whatever, it says error, can't divide by 0, which makes sense because you can't take anything and divide it into 0 groups or 0 teams or anything like that. So what we run into here for our domain is we can put anything else into this, any fraction, decimal, positive, negative, whatever. We can't put 0 in. So the way they usually write this, and there's a couple ways you can do it, but they usually write it like this, where they say x, they put this line, and they say x cannot equal 0. And so they define that as the domain. The x can't be 0. Other things you could say there, you could say, all real numbers except 0. It's writing it out in words. Here's a couple things you could do there. Now we also have the range. And in the range, we run into a little bit of an issue too, which is you also can never get 0 out of this function. Because think about it. Any number you put into here, no matter what you put in, you're going to get something that isn't 0. If you put 1 into here, if you put a million into here, you put a negative into here, there's no way this ever hits 0. So we actually get very similar domains and ranges here, where neither number can ever equal 0. And because of that, you get a pretty unique looking graph. Let's go ahead with this little table route first, like it says. So if you were to make a table of values, let's just say you're taking x and y values, and let's just do kind of the basics here. Let's do from like -3 to 3. And what happens is every time you put one of these numbers in, you get the reciprocal of it out. So you would get, -1/3, and you would get -1/2, and you'd get -1, and 0 we said is what we would call undefined. You put 1 in, 1 divided by 1 is 1. You'd get 1/2. You'd get 1/3. Now, if we just plot those points, we're only going to get, we're going to get 6 dots on here. So I'm going to plot those real quick. So we'd have -3, -1/3. We'd have -2, -1/2, -1, -1. Okay. Over here, 1, 1, 2 and 1/2, 3 and 1/3. So we get this, which is starting to look a little weird in terms of how you should connect that. So just to kind of show you a little more here, if you look at what happens to some other numbers, let's say we continued our table a little bit. So what happens when we do like a decimal? Like what happens at 0.5? Where does this go? So if you do 1 over 0.5, that's 2. So at 0.5, this graph is up here at 2. So what about like 0.25? So, like a quarter. 1 over 0.25 would be 4. And what happens here is this keeps getting higher and higher like this. And what you end up with is you get this curve that's bordered by your axes. And you'd get the same thing over here because you'd get like -2 and you'd get -4. And so what you get is you get this shape of a graph. Which is definitely a weird one. This is not, I saw this in the warm-up a little bit, but to get these two curves here is a pretty weird shape. But it does make sense in terms of our domain and our range. This graph, 0 doesn't exist for x, which is why as you start getting close to 0, the graph kind of wigs out and it goes completely vertical. And the same thing, you can never get a 0, I can't put a 0 into the graph, causes that same issue in the direction here. So it's kind of cool. So then I have a couple sort of little follow-up questions here. It says, what happens to this graph as it approaches positive infinity? So as you go towards positive infinity, as you keep going this way on the x's, the graph approaches 0. Or in other words, we'd say that the y value approaches 0. And then It says what happens as x approaches 0. So as your x gets closer to 0, as you go here and here and here, these graphs skyrocket or plummet to positive and negative infinity. So in this case, we'd say y approaches, I'm going to say positive or negative infinity. So we have kind of a weird little scenario going on here, and this is the basics of these reciprocal or rational function graphs. They're always going to have these curves to them, and your special names for those, like we talked about in the warm-up, is asymptotes. So we have a y-axis and an x-axis asymptote. So if you want to throw it in here, let's see, probably a good spot here maybe, asymptote. An asymptote is a line that a graph approaches but never touches. So a line that a graph approaches but never touches, which in this case, the y-axis and the x-axis fit the bill there. All right, so the nice thing though is as you mix these up and as you change up this function, if you look down here, this next one, they really just change that k value. They make that k value a 10 now. And so much like what we've done with every function, all of Algebra 2 so far, is this is like causing a stretch or a skew. So all this is going to do is make the problem essentially increase 10 times faster. It's going to have a 10 times bigger rate, or it's going to be stretched by a factor of 10. So I'm going to just write that down as a little note here. We're going to say it's stretched by 10. And I'm going to go ahead and jump right to the calculator here just to save us a little bit of time on some things. And if we graph this, just y equals 10 over x, you're going to see it's going to maintain basically the same shape. The only real difference is, our graph here was at like negative 1, 1 and 1, 1. What you end up with is these points are a lot further out. At 1, this graph's at 10 now. But it doesn't retain the same shape. It just gets that stretch to it. But other than that, it's going to have the same asymptotes and everything where, it doesn't touch the y-axis, doesn't touch the x-axis for the same reasons as the previous graph. So they ask things about like what's the domain and the range. Those aren't going to change. The domain still can't be x. So all x's except 0. I think I just said x, but 0. And the range, in the same way that it approaches but never gets to the 0 line here, that range is the same thing. You'll still never get 0 out of it. And that's going to be true for all of these until we start shifting the graph, which we'll see eventually. So, if we were going to draw this or sketch this or whatever, like I said, when you put 1 into this function, you'd get 10 out. So it's going to be like way up here. Same thing when you put a negative 1, you're going to get negative 10. But other than that, it's going to follow. I'm not going to make a extremely accurate graph. I'm just kind of sketch it on here. But it's going to follow the same kind of shape that we're going to notice in all these rational reciprocal type functions. All right, so you're going to use your calculator at times for graphing these, but the definite feel you want to get is it's going to maintain this kind of look to it where it's going to approach but never touch specific lines, the asymptotes. Okay, so as we move on to 5, so I just hinted at this, but now we're getting into translations. We're going to start shifting these graphs left, right, up, down. The beauty of this is it's the same thing we learned all first semester. These same concepts of when you affect the x directly, that's going to cause left or right shift. When you add or subtract something on the end, that's going to cause up or down shift. So going into this problem without any real knowledge about anything, we should be able to come up with the conclusion that this is going to shift it right 3, and this should shift it up 2. But when we say shift it, what are we actually shifting? Think of it as the asymptotes. Normally those asymptotes on our other graphs, those asymptotes crossed at 0, 0. So this isn't technically like the vertex of this graph, but it sort of behaves like the vertex, like in like a quadratic or whatever. If you move this point in certain directions, it's going to shift those asymptotes, and that's where they're now going to go. So in this problem, instead of my asymptotes being at, x and y axis, that 0, 0 point is going to shift right 3 and up 2. Now, this is not a point on the graph. Definitely not a point on the graph. I'm just kind of marking it there as my indicator. That point is where the asymptotes are going to go through. So I'm going to put a couple dashed lines through there. And at this point, my graph now is going to fit within there. And since there's no sign changes or anything weird here, I'm going to expect it to stay in these same coordinates. Stay in these same quadrants as here and here. And we can always pick a couple points in order to plot them. And, we can check it in the calculator. We can do a lot of stuff to make sure we're graphing the right thing here. But let's just pick like a, I don't know, pretty easy point. Let's pick like 4. Where's the graph going to be at 4? If I put 4 into this, 4 minus 3 would be 1. 1 divided by 1 is still 1. Plus 2 is 3. So 4, 3 is a coordinate. So yeah, so this coordinate's going to be right on here. And what we're going to get basically is the same shape that we're used to. And it's going to match it down here as well. So we're going to get this. As always, you can verify things with a graphing calculator, whatever, but you really got to be cautious with your parentheses. So if I'm putting this in, I need to make sure I put this x minus 3 in parentheses because that needs to be the entire quotient. To that, I can then add the plus 2 because the calculator will do the division first, then it'll do the plus 2. So this will work, and this should look like what we just drew on our paper there. And we can see those asymptotes vertically and horizontally here. Now we should be able to list where those are at because that's the first thing it says, what are the equations of the asymptotes? So key thing to remember, if it's a vertical line, it's an x equals. So it's going to be x equals 3. And if it's a horizontal line, it's a y equals. So that's going to be y equals 2 because it was shifted up 2. So those are my 2 asymptotes for that problem. Remember, vertical and horizontal lines are always just x equals or y equals a number. Also, what are the domain and range? So this actually changes things a little bit too. It's no longer going to be 0 and 0. You look at this and you say, well, x can be everything except my x can never be 3. Because if x is 3, my denominator would be 0. And then for your range, again, I like to look at it graphically here. What number can it never be? The y value you never get is right here. It's this y value of 2. And there we go. So the same kind of shifts we're used to with lefts and rights, affecting them just like we're used to with all our other functions, quadratics, cubics, stuff like that. It just applies with reciprocal functions too. All right, here's another example, same type of deal. So let's look at it and make sure we can figure it out. So by looking here, directly affecting the x, that's going to go left 2. And out here is going to go down 4. So if we go left 2, down 4, again, that's going to be kind of my, again, not a point on the graph, but that's going to be where I need to draw my asymptotes through. All right. And then, again, we should expect it to be in the first and third kind of quadrants of this, but we can always check a point because once you start changing signs up here, that will change some stuff. We'll see that in the next unit or next section. But, if we plugged in -1, -1 would give us 1. -4 would be a -3. So -1, -3, it's going to be this point. So we can see, yeah, it's going to have this this shape to it, which is what we're pretty much used to and pretty much anything we've seen so far. Again, I'm not making super accurate plotted things. We're really concerned about the asymptotes, the domain, the range, that kind of stuff. So for this problem, where are my asymptotes? X cannot be -2. So x equals -2. And y can never reach -4. And if you made the connection from the previous problem when we did the domain and range, you'll notice that these align perfectly with what we just did right here. So my domain, I can put in anything except -2. And my range, I can get out anything except right here, -4. And those will always correspond directly with your asymptotes because that's why they're asymptotes. They're asymptotes because those numbers can't exist on the x or the y planes. All right, there's a little bit of follow-up stuff here if you want to check this out, just kind of like summaries of the stuff we just talked about. You can use that or check that out as you need to. And other than that, hopefully assignment goes pretty smooth for you.